Good morning, everybody. Welcome to our 27th Global Online Seminar in Biodiversity Informatics with a history of visualization of biodiversity data. We have the good fortune of having Javier Otegui with us. Javi has begun a career in and already distinguished himself on global scales. PhD at University of Navarra, correct?
Mm-hmm.
And postdoc at University of Colorado, and now back in Spain. And so he's actually a repeat speaker. He gave one of the very first global online seminars, and we were just remembering that he's also the only person to have broken Google Plus Hangouts, so we're hoping he won't repeat that. Anyhow, just to remind you in advance, coming up next month on September 29th, we have a Global Online Seminar number 28, which will be on the history of citizen science in biodiversity informatics. Regardless, right now we see Javi's talk on the history of visualizations in biodiversity informatics. So I'll turn it over to Javi. I'll also remind all of the reviewers that you can send questions either by email or by Twitter, and Javi's put the links to both of those throughout his seminar. So Javi, all yours, and many thanks for the seminar.
Thank you, Tom. Thanks for giving me the opportunity again to contribute to this series of seminars. It's really an honor to present this seminar, given that I'm I'm still kind of a young researcher in this field because I finished my PhD in 2012. So as I've said, it's an honor to be presenting this seminar on the history of visualizations for biodiversity data. So without much more introduction, I'll just switch my screen. Okay, there you go. Can you see the slides?
Yes, we can see them. Thanks.
So just before I start, I want to remind you of the two ways Tom has said for sending questions. The first one is using the email address at the bottom left, the biodivtraining@gmail.com. And as a new feature, we also accept questions via Twitter with the hashtag AskBITC. So whenever you come with any question, please feel free to drop a line by either one of those. And at the end of the seminar, I'll do my best to answer any question. Also, before I start with the seminar itself, I would like to give a special thanks to all these people who have helped me building this seminar. They have helped me by pointing me towards resources, by describing me important tools, important projects, or giving me the best methodology to present the first and last improvements on data visualization. Data visualization is such a large field, and I'm probably missing many important events and projects, so I apologize in advance for that. And to start with the presentation itself, first the overview. I will talk about biodiversity data visualization, but one cannot talk about biodiversity data visualization history without talking a bit about data visualization history itself. So the first half or so of the talk will be focused on the history of general data visualization, while the second one will be more focused on the actual biodiversity approach to data visualization and graphic techniques over time. So the first and most basic question is, what is data visualization? How could we define data visualization? I read somewhere a definition that I really like about what data visualization is, and it's the graphical display of abstract information for basically two purposes. For sense making of the data that's being visualized, and also for efficient and engaging communication of that new sense. Both features are really important, are crucial. A good visualization provides some sense to the underlying data, shows something that was difficult or even impossible to see at a glance. And also, it needs to engage with the audience in order to effectively transmit or send this message. This, for example, is this comic strip from XKCD with all its fine irony is a paradigmatic example of a useless visualization. Even if it represents faithfully the underlying data, like the amount of ink and the position of ink on the chart, it really makes no sense. It doesn't really transmit useful information. This is a classic and real example of how visualization can help us understand better our data. This example is called the Anscombe quartet. And the idea behind it is that we have 4 data sets named 1, 2, 4 with a distribution of coordinates or points. If we simply see the statistic values, the statistic variables of this data set, we see that all the averages, sums, and standard deviations for each of the x's and each of the y's are the same. The values are actually the same. So in principle, just by looking at this, we could say that the 4 data sets are effectively the same. But what happens if we plot these 4 sets in different graphs? This is the actual look and feel of these data when represented. None of them is equal to the other, and some of them reflect better than the other the relationship between x and y. So data visualization, in essence, are one of the best tools to give sense to the loads and loads of available data nowadays. I've put here some quotes about visualization that summarize what it means and what are its ultimate goals. I particularly like the second one, which says visualizations act as a campfire around which we gather to tell stories. Because in the end, it's all about telling stories, telling good stories. Visualizations not only need to provide better insights, they also need to communicate those insights effectively. I'll switch to my browser and show you a couple of examples of really effective and engaging data visualizations. There we go. This, I hope you can see this one. This is a representation of migration patterns of birds near Belgium and the Netherlands. It's a really simple but effective and visually appealing way of representing movement over time. And I think this is a really cool example of a good visualization since it transmits the underlying data very well. The other example I want to show, and I'll talk about this later during the presentation, is this application called Krona. This is a static image of the application that that does a really good job in unifying, condensing, and showing metagenomic data. And on a customizable way, a user can go to the application and say, and play with the variables, with the graphic variables in order to show more or less. So going back to the presentation, let's begin then with the history itself of data visualization. I have divided the history into 6 periods, each one with a general feel or a background idea, which are ancient history previous to the 17th century, the 17th century, 18th and beginnings of the 19th century, the 19th century itself, 20th, and nowadays the last decade or so. Beginning with pre-17th century history, people have always used graphical methods to represent the world they live in, starting from the closest elements to mankind, such as food, or natural features, such as the position of stars in the sky. The aim of these graphics, of these visual representations, was to try to make sense of the world surrounding the inhabitants. Making maps was also one of the earliest forms of data visualization, with coordinates being developed by ancient Egyptians for the purpose of surveying towns, for example. This particular example here represents an anonymous plot representing the change of position of the 7 most prominent heavenly bodies that could be seen. It's considered to be the earliest graphical display of quantitative information. It's not only the statement of a fact in a moment, it gathers several pieces of data or information from different moments in time and tries to make sense of it all. The 16th century brought new techniques and tools to better observe and measure physical quantities and qualities of the environment. For example, to the left, there is a depiction of Tycho Brahe's large mural quadrant, which was basically a larger version of a regular quadrant for improved recording of position of heavenly bodies. This quadrant needed 3 people to be operated. We have the person here that's the actual making the observation, the one that interprets the position of the lens, and the note taker who's recording the values. It was very difficult to do it for a single person. Also, the first ideas on how to capture images arose. For example, the camera obscura was, which was the great-grandfather of modern cameras, was used in this case to record a solar eclipse. It's one of the first examples of recording natural features or events for later analysis. This map here, the Theatrum Orbis Terrarum by Abraham Ortelius, is considered to be the first modern atlas beyond previous efforts to record local areas such as the Egyptians. But this was to give you a brief idea of the tools and techniques that laid the foundations for the true beginnings of data visualizations, which took place on the 17th century, and basically came from the hand of this man, René Descartes, which was a philosopher, mathematician, and scientist. You know that people in history, people always have long names because they did a lot of work. But this particular man is known as the father of modern Western philosophy, of analytical geometry, and is a key figure in the scientific revolution. And it's important in our case because he developed, which was later called the Cartesian coordinate system in 1637. The original Cartesian coordinate system was based on one simple axis, one dimension. A measurement was taken in reference to one dimension. Later on, It was a matter of different scientist, Franz van Schooten, that introduced the second axis and therefore built what we nowadays know as the Cartesian coordinate system of 2 dimensions, but it was after Descartes' work. Also, in this period came the first ideas for more complex visualizations. This particular case, in 1626, Christopher Scheiners represented the sunspots over a period of time and made a particular effort in showing the difference in the position, the evolution of these sunspots by using a technique that was later called the principle of small multiples. These multiples show the evolution of certain features which are described in a larger version of the plot. In this case, to the top left, we can see a larger image of the sun with the main sunspots and some contextual information. A noteworthy example of visualization, which is considered to be the first visual representation of statistical data, came from the hand of Michael Florent van Langren, which was a Flemish astronomer to the court of Spain. At that time, the lack of reliable means to determine long distances was a real problem for navigation and for exploration. What Langrenus, which is the Latinized name of this man, what Langrenus did was that he took all the known estimates of distances made between these two notable cities, Toledo, which was the capital of the Spanish Empire at that time, and Rome, which was and is a really important place in the world. And he represented all the estimates along a single axis, along with the name of the person that made that estimate. It's considered to be statistical because it can be seen as the plotting of repeated measurements. By the way, all of the estimates were biased upwards. The actual distance in degrees of longitude between Toledo and Rome is 16 degrees and 30 minutes, represented here by the arrow. But still, it's a pretty good effort of bringing together all that's known and give it a more concise and easier to read sense. Even if there were these examples of visualizations, the 17th century wasn't really prolific in graphics and visual techniques, probably because of the lack of means and a low availability of data, which made it difficult to develop new plots and charts. However, by the 18th century, there are already several features that fostered the creation of new visualization methods. So I call this period the establishment of data visualization. Among these important features, we can find the development of some rudiments of statistical theory, a larger availability of data of interest and importance, and the idea of graphic representation being somewhat already established. This century witnessed the expansion of these aspects to new domains and new graphic forms. For example, one of the first elements that reflected these improvements were maps. Up to this point, maps were simply the representation of the places where places were in the context of an area. But with this gentleman, Edmund Halley, in 1701, he started adding more information to maps. For example, the contours or isolines to show equal value, lines of equal value on a coordinate grid. In fact, maps showing isogons are among the first examples of what's currently known as thematic cartography, which is overlaying data of any nature on a map. This century also witnessed the first steps of what are currently widespread charts. In this example here, we can see the first timeline chart used to represent the lifespan of different notorious people from ancient history. This plot was made in 1756 by Joseph Priestley, and it's a bit tricky to read at first, but it makes total sense. This axis here represents the year from year 0 backwards to year 50 before Christ, year 100, and so. And each line is an important person with its name up here and the date of the year of his birth and death. This plot here is considered to be the father of modern bar charts. But the real revolution of statistical plotting has the name of this gentleman, William Playfair. This Scottish economist is considered to be the father of graphical statistical methods and the inventor of most of the most common plots used today, which are the line chart, the bar, the area, and pie charts. All of these were first published in his work, The Commercial and Political Atlas, in the shape of 43 time series plots and one bar chart, which is considered to be the first major work containing statistical graphs. The problem of being the first one is that he had to devote several pages of this work describing how to interpret a line graph. This is one of the examples of such graph in which Playfair exposes the difference between imports and exports to and from England and Denmark and Norway. In this plot here, we can Playfair successfully shows that before 1754 or 55, there was a balance against England because the imports were higher than the exports, but that trend changed afterwards. Also, this plot over here is an impressive example for that time because it gathers 3 different plots in a single rather clever way of representing wages, prices, and the ruling monarch of England over a 250-year period. The line chart at the bottom shows the increase in wages for workers. The bar chart in the middle shows the prices of wheat, I think, and the timeline at the top shows who was the ruling monarch, the king, at that in those years. Even if nowadays it's considered a sin to use 2 different y-axes in a single plot, this is a good example of how to condense more related information into a single image. So by the mid-1800s, all the conditions for the rapid growth of visualization had been established. On the first hand, we had, they had, better said, official statistical offices that were established throughout Europe. Second, numerical information was growing in importance for all human endeavors. And third, statistical theory provided the means to make sense of large bodies of data. These developments were so varied that it is almost impossible to be comprehensive here. So I'll just show, excuse me, I'll just show the ones that stand out. And one of the examples that stand out is the birth of modern style thematic statistical map. This is the first known choropleth diagram or choropleth map, which was drawn by Charles Dupin in 1826, and it represents the degree of illiteracy in France divided by regions. Using a continuous shading scheme, Dupin Dupin represented this information in a way more better than simply an amount of tables or the existing charts. In the mid-1800s also, London was suffering a cholera outbreak. At that moment, the origin of the disease was unknown, and some people thought it was spread by air. But then came John Snow, who knew something, I guess, and mapped the cases of cholera outbreaks along with the distribution of water pumps. In this map, we can clearly see that black boxes are events of cholera, houses infected with cholera, and we can see that they are clustered around water pumps, in particular the pump in Broad Street. This led to John Snow to discover or state the fact that cholera was waterborne. And this is one of the applications, one of the first applications of thematic cartography to human topics, to health topics in particular. Also, this was the foundation for a future plot type called the Voronoi diagram, in which all points in an area are equidistant to its center. And this is considered to be one of the key innovations, or the key innovation, for modern epidemiological mapping. Another person of interest was Florence Nightingale, who in 1858 developed the polar area diagram, also called the Rose diagram or Coxcomb. And she did this in order to represent the causes of death in the Crimean War of England. With this plot, she was able to determine and to show effectively that most of the deaths in this war were due to poor medical care of the wounded people and were therefore avoidable. Another key person here is Francis Galton. He is well known in the statistical realm for his ideas of correlation and regression, but less known is the role that visualizations played in his discoveries. In this mega plot here, which is actually only a portion of the huge plot, we can see the atmospheric features of each day during the month of December 1861, which are the barometric pressure, the wind direction, and rain and temperature in different horizontal lines for the morning, evening, and morning, afternoon, and evening of each day of December in columns. Thanks to these observations, Galton discovered the anticyclonic pattern of winds around low-pressure regions, which were combined to clockwise rotation around high-pressure zones. Howard Weiner, a renowned American statistician, compared this work, organizing and giving sense to all these meteorological data, with what Kepler did with Tycho Brahe's set of celestial observations. It made sense to all the data that was available at that time. But if the history of data visualization can be condensed in a single figure, it's this one. This is widely considered to be the best statistical graph ever drawn. In this plot by Charles Minard, what's represented is the disastrous losses of Napoleon's army during the 1812 Russian campaign, which is known in Russia as the Patriotic War of 1812. Guess who won? In this plot here, there are 6 different data features represented. The general overview of the plot is that it describes the march and retreat of Napoleon troops from the Polish border to Moscow. So the first feature we have is the size of the army, which is the width of the lines. The second one is the direction, which is red when it's going to Moscow and black when it's retreating. The third one are the coordinates. The third and fourth are latitude and longitude. The fifth one is the name of the places. And the sixth one is the temperature in or around each point. As I've said, this is considered to be the best statistical graphic ever drawn. And by the way, some of you may have noticed that the main image for the data visualization series of Wikipedia articles is precisely this plot. Now, moving on, who knows if it was because of a generalized hangover, because of an exhaustion of ideas for new graphs, or a shortage of interesting data. But the fact is that if the second half of the 19th century was the golden age of data visualization, the first half of the 20th can be coined as the modern dark age of data visualization. Actually, the most likely reason is a shift of intellectual opinion away from visualization and towards more serious, formal statistical analysis, or so they call them. Pictures suddenly became simply pictures, incapable of stating a fact up to 3 decimal points. However, this period can also be seen as a period of necessary dormancy, where the methodology became more mature and more stable, and not an innovative period. But while the 20th century, and especially the second half, was a period of stabilization for data visualization, it saw the birth and development of another field very closely related to data visualization, which is the Geographic Information System field, or GIS. And for GIS, we have this gentleman here to thank. This man, Roger Tomlinson, was the pioneer of GIS software, and is actually the person who coined the term GIS in a paper in 1968. He was also the developer of the first GIS program, which was only released for the Department of Forestry and Rural Development of Canada. This software, the CGIS, was never released to the public and was only available for this department. This GIS, the Canada Geographic Information System, had all the basic GIS features. It had an underlying database to store information. It had software to manipulate and analyze the data in that database, and mapping tools to represent the outcomes of this analysis. Before this GIS, there were mapping applications, of course, but were only programs to represent data on a map. They didn't have the capability of overlaying, measuring, and digitizing, and most of them didn't have the underlying database to work with the data directly. Almost at the same time that the Canada Geographic Information System was deployed or launched, 1 year later, we have this man here, Howard Fisher, who founded the Laboratory for Computer Graphics and Spatial Analysis at Harvard Graduate School of Design. In his lab, a number of important theoretical concepts in spatial data handling were developed, and also some of the first commercially released GIS programs were developed, namely Grid, Odyssey, and SciMap. These are actual SciMap outputs. You can see that they are drawn using ASCII characters, with lines dividing areas being simply white spaces, and different colors are represented by using different density characters. The good thing about these maps is that since they are character-based, are very lightweight. So at that age where the internet was on its early stages, they could be easily transmitted via different protocols, such as HTTP, of course, but also Gopher, which was a text-based protocol, a protocol for sharing text-based files. Going back to the visualization and leaving GIS for a minute, now come two VIPs who wrote a groundbreaking book each. The first one is Jacques Bertin, a French cartographer who discovered that visual perception operates according to a set of fixed rules, and those rules can be followed in order to better express information. This book is called The Semiology of Graphics, and is one of the theoretical foundations of information visualization. Our second crucial writer was Ian McHugh, a landscape architect who wrote the book called Design with Nature. This one was crucial for the development of GIS because it pioneered the concept of ecological planning for land use development and established a set of basic concepts that would be at the core of modern GIS software, such as overlaying transparent maps. This is the cover of that book. The late 70s also saw this man pushing the field forward, the field of data visualization, formally. John Tukey, apart from his copious contributions to statistical, was a data visualization hero. He developed a whole new branch of statistics based on visualization called the exploratory data analysis. At that point, as we have said, graphics and pictures were near useless because they weren't able to significantly state facts. However, this man here developed a set of visualizations and techniques to give greater importance to these visual methods and show that these methods could summarize faithfully the main characteristics of data sets. But if one name stands out of the rest in nowadays information visualization, that is Edward Tufte. Tufte is the person with the greatest understanding of how data visualization works at all levels, beginning from the graphic representation itself to the human comprehension and the understanding of the meaning of each of the features. His book, his 1983 book, The Visual Display of Quantitative Information, is a must-read for anyone attempting to approach the information visualization domain. The main idea of this book is that there are two ways of representing data: the good way and the way most people are doing. He also offers some guidelines on how to create effective and engaging visualizations. During these years, and going back to GIS land, with the first commercial GIS software released, several different initiatives are created that develop and offer their own GIS programs. During the 70s, we see the creation of two key open source GIS programs, MOS and GRASS. While during the 80s, it's the time for the commercial and closed source enterprises. Among others, 1982 saw the birth of the Environmental Systems Research Institute, which are the creators of ArcGIS. Also in 1982, this company released the first version of ArcInfo, which is a somewhat ancient GIS software only available for mainframes. Due to the low availability of computers at that time, only universities and large research institutions could afford buying and maintaining a mainframe, and therefore GIS was restricted to these domains. However, in 1986, things changed with the release of Mapping, Display, and Analysis system for DOS operating system, which is known to be the first desktop GIS product and looked pretty much like this. Remember that the IBM PC, which is considered to be the first true widespread PC, was released in 1981, so it came in the best moment. This MIDAS system was a DOS-based program operated by commands with very low resolution and very low color capabilities, but it could still do its job. For those of you who are curious, there's a link down here which points to a YouTube video showing a demo of the second version of MIDAS, which was later renamed to Map Info for Windows. This video is from 1988. And while even if Esri didn't release the first desktop GIS, what they did release was the first GIS with a graphic user interface in 1992, which is the ArcView. All these developments in graphic techniques, visualizations, theoretical foundations, and computing tools set the ground for the solidification of a new domain, the information visualization. It was no longer a matter of representing data, which now abounds. It's about finding the right way of transforming this data so that the underlying story is revealed. It's about visualizing the information beyond the numbers. So far, all scientific work related to information visualization was confined within the walls of academia. But these three gentlemen here gathered all relevant writings on the topic and published yet another groundbreaking book, Readings in Information Visualization Using Vision to Think. This was a keystone moment because it allowed people outside the academic world to know about this emerging field, people such as engineers, journalists, or even the general public. But even if the theoretical baseline for information visualization was being well established, there was a lack of practical background, especially in computer-based graphic representations. That happened until this gentleman here came and published the Grammar of Graphics, a 1999 book establishing a solid framework for developing effective visualization with computer-aided tools. It is not intended to show the actual implementation of those rules, but to show the underlying nature of the different elements of visualization. The book has served, however, as inspiration for the development of several tools to create and manipulate graphical visualizations, mostly in the form of extensions to programming languages. The single most well-known package, depending on this book, is R's ggplot2. This package, developed by Hadley Wickham, is one of the most downloaded and used packages for this language, and is basically a line-by-line implementation of Wilkinson's ideas into R functions. There are also certain modules available for other programming languages, such as Python, that follow the rules of the grammar of graphics, like Bokeh or Yhat's implementation of ggplot. Nowadays, the field of information visualization is widespread, and there are different solutions for different scenarios. We have seen some of them in the form of extensions of programming languages, but there are many more kinds. For those non-programmers, there's a plethora of tools that allow building, engaging, and effective visualizations. Here are only some of them, the ones that are most commonly used. Perhaps the most famous one is Tableau. This is actually a complete data analysis suite based on visualizations and giving an extra strength to visualizations. This program allows users to load data, build some workflows for manipulating them, and create visually appealing plots or charts. Even if it's a proprietary program, it's becoming the de facto standard for building complex data visualizations. An open source alternative to GIS software, and the one that is gaining more attention lately, is QGIS, formerly Quantum GIS. It has all the GIS capabilities one could expect, and since it's open source, it's easily extensible and customizable. The Biodiversity Informatics training curriculum website has a set of video tutorials on the use of QGIS. And there are many more. Among others, I'd like to highlight Pattom, VStraits, Gephi, Gapminder, or Axis. But there's even more. Apart from programming languages and desktop tools, online web-based visualization are of great importance today, especially to be able to communicate widely these graphs. D3, for example, is a JavaScript library for manipulating, for creating and manipulating visualizations based on data. D3 is probably the most flexible tool for this kind of visualizations, but it has a steep learning curve, and it can be a bit cumbersome and time-consuming. So there are other easier or more convenient options, such as Google Charts, which is another JavaScript library which pretty much does the same, but easier. And for more particular cases, such as in this case, geographic location and mapping, we have services such as Carto, previously known as CartoDB, which is a database, cloud-based database with mapping capabilities. Last but not least, here a special mention to this incredible tool, Shiny. Shiny is an extension to the R programming language that enables fast and easy creation of web visualization applications. It's basically a web server and a language to build dashboards to represent data. And since it's linked to R, anyone can turn their dataset and analysis output into beautiful and aesthetically pleasing web applications. So far, so good. Running a bit late, but we have seen already the most important remarks in the history of data visualization. But what happens with the development of visualization in our field, and why is it important? According to Arthur Chapman in the 20th online seminar, Biodiversity Informatics involves the use of modern technologies to convert vast amounts of data to knowledge, wisdom, and environmental outcomes. Visualizations are key to this process, quoted by Arthur, since they are a great tool to transform data to knowledge. So it's evident that visualization plays a key role in biodiversity informatics, especially in these three domains here: scientific publishing, actual research and data analysis, and reporting and decision-making, which is also known as data journalism, at least the reporting part. But how well has this role been performed over time? How has visualization performed over time? In order to keep it compact, I won't go far back in history, but far enough to see how things have changed. Maps are the most evident element to check how time changes. These maps, published in the 80s, in black and white and with low resolution, are a clear example of how scientific mapping was done back then. Many times, maps were drawn by hand, and more complex representations included overlaying transparent films with different data each. The absence of color made it difficult to represent more than one type of feature. Most of the times, figures were not clear enough, or they were color photographs that lost most of their complexity and information when printed in black and white. Plotting multivariate data was also a challenge due to the same limitations. Again, many times authors had to rely on their own pen and paper to build complex graphs such as the one to the left. And even when computer tools were available, many times the outcome was too complex to be visually appealing. Printed journals were the ones ringing the bell, and graphic visualizations had to obey a set of rules, many of which were purely practical, and in many cases, authors were limited to a small amount of pictures in order to save space and money. But then the new century came, and with the explosion of computers and internet, journals, or the authors better said, started shifting towards more complex and feature-rich visualizations. Many articles were published encouraging other authors to start using advanced tools such as GIS. Others published developments and ideas on the theory of data visualization. And the idea of workflows began to emerge in scientific literature. It was a matter not only of doing analysis, but also of publishing how to do more or more complete or better analysis. These methodological meta-articles started gaining importance and were the key to the advancement of the field. With the possibility of online publishing, many authors started building colorful maps. Also, the increased computing power enabled larger scale and more detailed analysis, but usually not both at the same time, or at least having both features was not readily available for everyone. Taxonomic and molecular papers were also significantly improved with the development of modern technologies and with the creation of specific software packages. We'll talk about this in a minute. And again, more complex and/or larger analyses were being carried out. Also, papers started publishing non-conventional figures, such as this word cloud here. In some cases, the importance of significance started to decrease in favor of unveiling patterns, general patterns and trends in the data. The last 5 years have witnessed a huge popularization of visualization in scientific papers. Publishing figures became easier, and so became analyzing large sets of records. So the next logical step was to develop tools to ease and automatize these assessments and visualizations. The publication of software description took off. In fact, there has been a shift from using tools to publish results to publishing tool descriptions. Some journals have enabled editorial lines covering this new type of article, and there are even full, complete journals dedicated to them. Since it's so easy to produce beautiful and meaningful individual figures and to create tools to gather, analyze, and display information, the trend moved towards aggregating all of them in dashboards. The publication of these type of data portals is increasing, and so is the publication of larger scale and higher resolution analysis. Visualizations are now so common that there is a new pattern here, a shift towards using multiple charts to compare instead of simply inform. Taxonomic research has also benefited from these improvements. Here I show an application to build really remarkable visualizations. The corona I showed earlier, circular tree maps to visualize metagenomic classifications. Building this, be it the plot or even more the tool, would have been impossible just a few years back. Moving on to the research and data analysis domain, visualizations have also been a key part of this process. There are several projects specifically aimed at building tools to visualize large sets of biodiversity data. The most preeminent ones are shown here. And the outcome of these projects, apart from scientific papers, were desktop programs and later web services. Here I'll show some examples of each. The first one, the first desktop program, which was an outcome of the first project, the one from the University of Maryland, is Taxon Tree, which is a software for easy visualization of hierarchical data, such as taxonomic classifications. There's an extension to this program called DoubleTree, which allows also to compare two taxonomic trees using couple interactions. Another program that derived from a research project, is FloraMap, published by the International Center for Tropical Agriculture. This is a system basically to predict potential distribution or areas of possible adaptation of organisms. It uses environmental variables of the presence locations of organisms to calibrate and compute a climate probability set. A special desktop software, well known by many, if not all people in biodiversity informatics, is DivaGIS. DivaGIS was built by Robert Heidmans and is basically a GIS software with enhanced features for biodiversity research, such as links to species occurrence data, gene bank collections, gazetteers to check locality information, or an ecological niche modeling tool, and also functions to calculate richness and diversity measures. It's also linked to two wonderful and freely available datasets, the Global Administrative Boundaries and WorldClim for world climate data. Now, moving to the online services, one example of such service for the biodiversity informatics domain is MapStudy. The idea behind this project was to convert several collections of biological data from the southern and central Rocky Mountains into a single biodiversity database and research toolkit, which implemented a mapping tool. Unfortunately, and as happens with many of these web-based solutions, it is now offline and can no longer be accessed. A tool that needs special attention is the Berkeley Mapper from the University of California, Berkeley. Started in 2004 with the aim of mapping natural history collections, this piece of software was available before Google Maps API and tiling were available. So this was a really huge task. It used configuration files to prepare this mapper for specific collections and offer a full map view for the information in those collections. When the Google Maps API was released, the project was rewritten to leverage that source. Nowadays, the project is still available, the tool is still available, although it's used primarily for Berkeley collections. Apart from these examples of thematic visualizations, since 2012, there have been several attempts to offer what I like to call visualization suites. The pioneer here was BITC, a now obsolete tool I created in 2012 to visualize the content of the GBIF database according to different parameters. Time has enabled the evolution of this concept, and the recent Vesper is an example of a more mature and up-to-date Darwin Core Archive visualization suite. Actually, the visualizations are the same in nature, but much more modern and customizable. Finally, visualizations are a key component of reporting of results and influencing decision makers. There is a whole subdomain called data journalism that focuses on this aspect of building visualizations to inform rather than doing exhaustive analysis. Biodiversity informatics has seen the development of field-specific plots, such as these two. The Voronoi diagram, which is the natural evolution of the tree map, is useful for representing taxonomic hierarchies. And on the other hand, the chronogram is a simple yet complex plot to show at a glance all date-related information. This plot uses a radial pattern to reveal abundance of features in time. The same as with desktop software, there are online services aimed at building comprehensive and precise thematic visualizations for the biodiversity realm. One of these is Map of Life, a project with the aim of being the reference in biodiversity information mapping. Map of Life links several data sources, such as museum collections, citizen science or observations, the IUCN and Red List of endangered species, and geographical data sets. All this in order to provide a comprehensive overview of the known information for a given species. Plazi, the Swiss-based non-profit, also offers a set of tools to visualize its content. The data in Plazi focuses on taxonomic treatments, and they are specialized in extracting information from taxonomic papers. And among the tools they offer, there is a visualization toolkit to get an overview of the information they gather about species. And finally, on the cutting edge, we have interactive dashboards. For years, initiatives and organizations have gathered information, occurrences, distribution maps, etc. And there was a time where reports on the content were generated at certain points in time and were basically extensive PDFs or web pages with tons of numbers and very few graphics. But with all that we have seen so far, the logical step was to build dashboards condensing and visualizing all the information in these data portals. I'll show 3 examples of such dashboards, all linked to large initiatives gathering and or publishing biodiversity data. First, we have the Spanish node of GBIF, which was among the first ones to create such dashboards. The Atlas of Living Australia is another example of a similar, yet more modern dashboard. Both this and the previous dashboard offer an overview of the content of their networks. The last example is different in the sense that it doesn't show the what's in the network, but rather how people use the data. The usage dashboard from the VerteNet data portal, the network of vertebrate biodiversity collections, show how many queries and downloads have been performed to the portal for a given period of time. It's nothing too fancy, but it enables seeing in a glance how people are actually using biodiversity data. I would like to end this presentation with a quote from Google's chief economist, Val Herian. The ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, that's going to be a hugely important skill in the next decades. He said this in 2009, and time is giving him the reason. It has been a wonderful journey so far, but as it is said, the best is yet to come. Thank you so much, and that's the end of my presentation. Town, I hand it over to you again.
Thank you, Javi. That was great. I will encourage all of our listeners to send in questions. And in fact, I'm seeing one from John Wiczorek. I saw one for a moment. Let's see. Let's see. Give me one moment. Everybody, send in your questions soon while we have Javi online.
We never know how much we'll be.
John's question is a very insightful and challenging question. He said, fascinating, really enjoyed this.
Thank you. That was the question.
That was the question, sorry. So I tweeted you a question, but I'm not seeing, there it is, yeah. Isn't that great? I tweet you something that I have to mention it to you that it's there.
Okay, let me check. Did you see the hashtag, the Ask BITC hashtag?
Yes. So
okay, there you go. Geographically, where was GIS first adopted and used in biodiversity science? Australia, Mexico, or where? That's a good question. I think, well, I wasn't there to check it, but I think that since the Canadian Geographic Information System from Roger Tomlinson was the first GIS software, and it was used to work on Canada lands to the development of rural areas of Canada. I would say that the thing that you said was used in biodiversity science, if we can assume that land use change and resource management is to some extent biodiversity science, then I would say Canada because of this.
Interesting.
Otherwise, I don't know. Actually, yeah.
In Arthur Chapman's and Jorge Soberon's talks about kind of history of biodiversity data management, both of them presented examples going back to the late 70s, and it was those character-based maps, and it was GIS analysis. It was just very, very hard to visualize when your pixels are several meters, several millimeters by several millimeters.
Right.
I think what you've shown really helps to appreciate, in many senses, how much easier things have gotten now that we can do these visualizations in seconds.
That's right. Yeah, nowadays almost anyone can build gorgeous visualizations with so little actual programming skills or design ideas, thanks to tools and services such as the one I have said, like CartoDB, for example. That's pretty easy, which in turn makes it easier to keep advancing on the field and build more and more complex and beautiful visualizations and infographies.
Definitely, definitely. Well, I'm not seeing any more questions, I'm afraid. So
I'm glad my talk was so clear.
It was, actually.
Thank you.
Thank you so much, Javi. And to our broader audience, I'll remind you again, I believe it's September 29th. We have our next seminar, which will be from Steve Kelling on the history of citizen science applications in biodiversity informatics. That'll be 9 a.m. Central Time, so Chicago time, on Thursday, September 29th. But again, for now, thanks so much, Javi, and I very much appreciate your time.
Yeah, thank you for inviting me again, and thank you all for listening.
All the best. Thanks.
Thanks. Bye.